Oh, good, you're here just in time. Look, we've got a bit of a situation. So, vertex T seems to have caught fire. I should have known this was going to happen. So, vertices are notoriously flammable. And this is a pretty delicate situation because I've been keeping all these vertices next to each other in this graph. So, if we're not careful, this fire could spread. Now, on the other hand, the worst thing to do in a situation like this is panic. And to be honest, I have been preparing my entire career to deal with an emergency like this, so I've already made a few preparations. I've already made some arrangements to allow us to put out a fire if a fire like this is to start. So for one thing, I've arranged for vertex S to be positioned next to this huge body of water. So if we can find some way of getting the water from vertex S to vertex T, I think we can put the fire out. And second, I've created this network of pipeline links between vertices. Now, each of the links in my pipeline has a different capacity. So for example, I can transport up to 5 units of water from vertex S to vertex V1. But I could also transport up to 25 units of water from vertex S to V6. And each of the links in my pipeline network has a specific capacity that is specific to that link. If I want to, I can route water flow through my network from vertex S to vertex T. So vertex S has basically an unbounded supply of water. I can take as much as I want. And vertex T has basically an unbounded demand for water. Really, my goal is to get as much water to vertex T as possible. So one example of a way I could route water through my pipeline network is I could send 3 units from vertex S to vertex V1, and then the same 3 units to V2, and then V4, and all the way to vertex T. So those 3 units end up at vertex T. I can route any amount I want as long as I respect the capacity of each link, and of course the direction. So in this case, the link from S to V6 can carry water in that direction only. I'm not allowed to route water from V6 back to S because there is no link in that direction. I can route a fractional amount if I want, so I could route 1.5 units. If I wanted to, I could even route some irrational number, like pi units out of 25, although, maybe I'd rather not think about that case for now. Now, besides vertex S, the other vertices in my network don't have access to a supply of water, and in fact, they also don't have any storage capacity. So while I can take as much water as I want out of vertex S, I'm not allowed to take water out of a vertex like V2 or V5 unless I also bring that water in. So if I want to take 2 units of water out of vertex V1, I have to also bring in 2 units of water somehow from vertex S. And similarly, if I bring water to a particular vertex, so for example, if I arrange it for 2 units of water to arrive at vertex V4, there is no storage capability at vertex V4. I have to route the water onward all the way to vertex T, where of course it can be put to good use. So one way of framing this constraint is that all of the flow that enters vertex VI must leave vertex VI. Now that rule doesn't apply to vertex S, which has access to this water source, and it doesn't apply to vertex T, where I can throw as much water as I want on the fire. So in other words, it is not permitted to create any kind of net shortage or surplus at any of these vertices in the middle of the graph. So for example, I couldn't take this path from vertex V1 to V7 and just pull 2 units out of V1 and send them to V7 for 2 different reasons. So one reason is, where am I getting this 2 units from in V1? How am I able to pull 2 units of water out of V1 when V1 itself has no access to a water source? The other issue is, what am I doing with the 2 units of water at V7? So I get 2 units into V7, and then what do I do with them there? Do I just dump them out? I have no facility to do that. So the only destination for water ultimately has to be vertex T, and the only source for water at the beginning must be vertex S. So if I want to route water from V1 to V7 in this way, I can do that as long as I find some way of bringing the water from vertex S to V1 and then sending it from vertex V7 onward to T. So for example, I could do something like this. I could route 2 units from S to V1, then I could follow the path I already gave, and then I could take those 2 units from V7 and route them onwards to T, resulting in T then receiving a net of 2 units of water. Now I'm also allowed to route flow along multiple routes concurrently, so we'll keep in that routing I already had, so that 2 units going to V1 via V7 to T, but I'm not required to use only one path at a time. I can try and saturate all of the links of the network to the extent that that's allowed by the capacities given by each link. So I could keep the routing I already have and add more. So with the flow values that I've set as above, vertex T is receiving a total of 2 units of water from vertex S. I could also choose this path here, and I could add some water along this path, bringing the total coming into vertex T to 5 units. If we compare this to what I just had, notice that I was already routing 2 units up to V1, and then down through T via this route here. If I then choose to use this path, I can add an additional 3 units going up to V1. Notice that once I do that, the edge SV1 becomes saturated. It will no longer be possible to put any more water into this link of the pipeline. If I push those 3 units onward to T via this sort of circuitous path, notice that none of the links along the way get saturated. The only reason I had to stop at 3 units was that the first link in the path that I chose couldn't handle any more than 3 extra units before it became saturated. So I could go looking for other paths. None of them could involve this edge because this edge is now full, but I could go looking for other paths that would allow me to push even more water from S to T. So for example, I could try this path here. It's a little bit roundabout, but I could push 3 units down from S to V6, then the same 3 units up to V5. You might be asking, why am I using only 3 units here? I take those 3 units up to V1, and then I bring them across to V2 and all the way over to T. Notice that this link here is saturated. So if I had tried to push any more than 3 units along my path, this would have become overfilled, which isn't allowed. The maximum number of units I can bring across this link is 5. Before I made that change, there were already 2 units being sent across that link, and that's why I had to stick with only 3, because that was the maximum number that this edge could take before becoming saturated. And then I could route some flow along this bottom route here, bringing the total amount I'm taking to vertex T to 11 units. And obviously, it's my goal when I solve any problem to do it right. It's important that I take pride in my work. I want to make sure if somebody gets me to solve any algorithm problem, and this is beginning to look sort of like an algorithm problem, that I solve it in the best possible way, in the optimal way. It's of course important that I put out this fire, and the best way to put out this fire is to bring as much water into vertex T as possible. So the question is, what is the maximum total flow that we can route to vertex T? I'm bringing in 11. I guess that might do the trick for now, but I want to know whether I can bring in more. I want to make sure this job gets done right. And it's really important to me that I do the job right, so I think that, we need to take a step back. It's important not to panic. We need to take a step back and think about this question a bit before we proceed. So let's just ignore the fire for now. We'll sort that out in a minute, but let's work on formalizing this problem so that we can make sure that when we go to put the fire out, we are sending as much water as possible to vertex T. I don't want to end up sending a suboptimal amount, then having to wait like 10 hours for the fire to go out. That doesn't make any sense mathematically. So I guess the very first thing I'm going to need to formalize is, what is this unusual looking graph that I've created? A graph that has a water source at one end and a destination with a huge demand for water at the other, and a bunch of vertices in the middle connected by individual pipeline linkages. It turns out this thing is called a flow network. And it certainly looks a lot like an edge-weighted directed graph. And many sources will define it as a certain type of edge-weighted graph, and that's fine. The key thing to understand, though, is that these labels that I've put on edges aren't single values. It's not like this is meant to be the fraction 0 over 10. Because if it were, we could just say 0, because 0 over 10 equals 0. Really, this edge label actually is 2 separate values. It's the capacity of the edge, the number of units of water I can send, and it's the flow across the edge, the number of units I currently am sending. So really, it's like an edge-weighted graph with 2 weights per edge that have certain constraints that apply to them. Every flow network has 2 special vertices. There is a source vertex called S and a sink vertex called T. And these are universal names. So if you open up any book that talks about flow networks, it is pretty much going to call the source vertex S and the sink vertex T. On these slides, I'm always going to color the source vertex blue and the sink vertex orange. And that coloring is just my choice to make them easily distinguishable among all the other vertices. And we're going to follow a convention of naming the other things, all the vertices in the middle. We're going to call those intermediate vertices. And although for a particular problem that we might be modeling, the actual identities of these vertices might be significant, for the sake of these examples in this lecture and the next one, I'm pretty much going to treat all of these vertices as sort of indistinguishable. That is, we have to give them names because obviously this vertex is different than this one, but they have no other greater significance besides just being places that I can go in the graph. So I'm going to call them intermediate vertices, and I'm going to label them just with numbers, V0, starting at V1, V1, V2, V3, and so on. So every edge in my network is, and we can see it's a directed edge, so flow can only go in one direction. Each of the edges is associated with a capacity value. Now, I just said that flow can only go in one direction. That is to say, it must respect the direction of the edge. But there could be individual pieces of the network where bidirectional flow is possible. So for example here, just leveraging one property of directed graphs, I am allowed to make edges pointing in opposite directions. And this does mean that I have the option of sending flow from V5 to V8 or from V8 to V5. Notice that the capacity of these edges happens to be different, and that's fine. So the capacity value that we associate with each edge is some number greater than or equal to 0, some non-negative capacity. Negative capacities are not even considered for this modeling of the problem. For the sake of this lecture, or at least the way that we treat this topic in this course, we are basically going to assume that the capacity values are integers. I'm going to come back to that point near the end of this lecture because certain weird things happen if we allow the capacity values to not be integers or rational numbers. So for example, if I allow edges to exist with capacity pi, then something strange could happen. But fortunately for us, not only because this seems sort of weird to do so, but actually because representing truly irrational numbers inside of a computer is sort of non-trivial. That is, a floating point number, which is what we usually use to represent real numbers, wouldn't suffice to truly represent an irrational number like pi. So it turns out that I think it's reasonable to assume that our edge capacities are going to be integers, or maybe at worst rational numbers. And I'm always going to draw the capacity as the second number in the edge label. And pretty much for our purposes, that's sufficient for visualizing it. Although if I want to talk about capacities in a proof, which I will, then I do need some notation for it. So we'll actually model capacities formally as a function that takes two vertices as its inputs and gives us back the capacity of the edge between those two vertices. So for example, the capacity of the edge from S to V1 is equal to 10 here. And as a notational convenience, because I want to be able to talk about the capacity of the edge between two vertices, even in the event that that edge doesn't exist, I'm going to actually define right off the bat that if I ask you about, if we want to talk about the capacity of a non-existent edge, so let's say I wanted to ask you about the capacity of the edge from V1 to V6, and you'll observe that there is no edge from V1 to V6, we will simply define that to be a capacity of 0. So we'll treat non-existent edges as if they're sort of hiding in the background and have capacity 0. As you will see as we formalize this problem, an edge with capacity 0 is essentially useless to us. And as a result, notice how none of the edges in this graph actually have capacity 0 because I sort of treat edges with capacity 0 sort of as the converse or the opposite of this situation, which is that just like an edge that doesn't exist can be interpreted as having capacity 0, an edge that actually has capacity 0, we can sort of treat it as if it doesn't exist because we can't send any flow across it, so it's pretty much useless to us. Now, what about actually sending flow across edges? Now, the word flow gets really overloaded in this topic because we've already talked about how the whole graph is called a flow network. And in a minute, I'm going to define the problem that we're really trying to solve as the maximum flow problem. I also want to talk about flow across a particular edge or the collection of flow values in the entire graph. So that's going to be difficult because it's the same word that I use for all of those cases. In any event, when I talk about a flow, really what I'm talking about when I say a flow, not like the flow across this edge, but a flow, just as a single object, I typically mean the assignment of flow values to all edges in the graph. We'll model those by using this function f. And just like the capacity function, I'll typically represent the flow values by just drawing them on the graph, but formally this means when I say that there are 9 units traveling from S to V1, really what I'm saying is that the value of f of SV1 equals 9. So a flow is a function that maps pairs of vertices to numbers. We'll see in a minute that for the flow to be valid, or the word I would prefer to use is feasible, certain constraints must apply to it. So one big constraint is that if I want my flow to be valid, the amount of flow I'm pushing across an edge cannot be greater than the capacity. So while it would be, I am technically allowed to define a flow that has some invalid amount, so I could say the amount across edge S to V1 is 100. I could define a function that has this property. We would not consider this flow to be feasible. It doesn't meet the necessary constraints. So although a flow formally corresponds to a function that takes two vertices and returns a number, or returns some value that's comparable at least, I will typically just call this number here the flow on edge SV1. And so I will always draw the flow across each edge as the first number in the edge label. Now, the ultimate problem that we're really trying to solve is how much flow can I get from vertex S all the way to vertex T? And if I stare at this for a minute, what I realize is the amount of flow leaving vertex S, at least net, is, well, 9 units leave, but then 2 units come back for some reason. Now, I don't know why I would want to do this, but I suppose this should be allowed. If I want to send flow back into S, to return it for some reason, I guess I should do that. But what I'll observe is what that really means is the total amount of flow actually leaving vertex S is actually 7 units. I do send 9 out, but for some reason 2 make their way back, so I assume that those are lost. It turns out also, if I stare at what's happening over here at vertex T, notice that I've got 12 units coming in from this direction, 5 units coming in from this direction, and then 10 units leaving vertex T. Now this also seems sort of counterintuitive. Why would I send flow back out again if my goal is to get it to vertex T? But I suppose I should be allowed to do that. I'm allowed to use my pipeline network however I want, although for the sake of my optimization problem, this thing does look a little bit suspicious. But notice that the total amount of flow, the net amount arriving at vertex T is 7. So vertex T is receiving a total of 7 units of flow that it gets to keep, and vertex S is losing a total of 7 units of flow that make their way onto vertex T. So what's really happened here is I've assigned flow values to each edge, and some of them are a little bit counterintuitive, but in any event, some of it does make its way all the way from vertex S to vertex T, and we want to call that amount the value of the flow. We're going to denote that by this notation here. In terms of giving that a solid numerical definition, I am going to define the value of a flow to be the net amount of flow exiting the source vertex S. Now in this graph, we observe that 7 units exit the source vertex S and 7 units arrive at the destination vertex T, at the sink. It turns out that if the flow meets the necessary constraints, we can expect that that will always hold. But as I said earlier, we can define flows that don't meet the constraints, that have invalid values, for example, sending 100 units across a particular edge. So for the sake of having one consistent definition, it will be the amount of flow exiting the source vertex S, the net amount. I can compute that by taking every edge out of the source vertex S to some other vertex, some outbound neighbor of S, adding up the flow across those edges, and then subtracting all the flow from other vertices back into S. So for example, here I would take the total amount exiting vertex S is 9, and the amount entering it again is 2, so the value of this flow is 7. The value of a flow will be positive, and that's one of the reasons we use that sort of absolute value symbol there. On my diagrams, I typically like to represent the passage of flow between vertices with assigned values. So in this case, because 7 units are leaving vertex S, on my diagram, I'm going to write that as -7. That is, vertex S is losing 7 units of flow. And I will also write over at vertex T that it is receiving 7 units of flow. So I use negative and positive signs to indicate which direction the flow is going. However, to be clear, the value of the flow itself, the value of F is equal to 7. There's no negative sign there, so it's just equal to 7, the net amount exiting vertex S. Now, I mentioned a minute ago that the flow function itself could be defined to have invalid results. So for example, the flow from S to V1, I could define a flow function that tries to put 100 units along this edge. And we can see that this does not respect the capacity. So we should now talk about what does it mean for a flow to be feasible, that is, to meet all of the necessary constraints. Really, there are just 2 constraints. The first constraint, the sort of obvious one, is that edge capacities must be respected. And so a flow is feasible. One of the conditions required for a flow to be feasible is that the flow across every edge must be somewhere between 0 and the capacity of that edge inclusive. So I could have a flow of 0 out of 10 on this edge, I could have a flow of 10 out of 10 on this edge, or anything in between, but that's it. I'm not allowed to have a flow of -1 out of 10 or 100 out of 10. And remember that it is technically possible to have a flow that's fractional, so 9.5 out of 10. Although we will observe later in this lecture that as long as the capacity of every edge in the graph is an integer, then it turns out that you will be able to work only with flows where the flow values themselves are also integers. Somebody else could define flows that are fractional. We'll discover that we don't really need to worry about such things as long as all the capacities are also integers. So one of the constraints we care about for a flow to be feasible is that edge capacities are respected, but not just that. I also have to define what I do with flow at intermediate vertices. So as I mentioned earlier, these intermediate vertices do not have any capacity to store water. So anything that comes in must leave. Additionally, they don't have access to a water source of their own. So if I want to take 2 units out of vertex V1, I need to make sure that 2 units enter vertex V1. And we can frame that in terms of a constraint that I'm going to call conservation of flow. So conservation of flow says that at any intermediate vertex Vi, the net amount of flow entering the vertex must be 0. And similarly, the net amount of flow leaving the vertex must be 0. In other words, whatever flow comes in must also go out. We can write that constraint in 2 ways. So one of them is to say, if we take all the flow entering vertex Vi and subtract off all the flow leaving vertex Vi, that number should be 0. Another way of framing it is to simply say that the amount of flow entering vertex Vi must equal the amount of flow leaving vertex Vi for all intermediate vertices Vi. We can quickly assert that if we look at this flow assignment here, there are, 9 units entering vertex Vi, and there are 2 plus 4 plus 3 equals 9 units leaving vertex Vi. So at vertex Vi, conservation of flow is satisfied. So these are the only 2 constraints that we need to satisfy for a flow to be considered feasible. The constraints must hold in the case of the edge capacity constraint for every edge, in the case of the conservation of flow constraint for every vertex. Okay, so is this a feasible flow? Now, I concede that checking these constraints is not fun. It is quite tedious, and unfortunately, apologies in advance for this, you can expect to have exam questions that are, look at a network that's this size or bigger and tell me whether or not the flow is feasible. Sorry about that. It is also error-prone because there's so many small things to check, so double-check your work. So let's walk through this and see if we can detect whether this flow is feasible. To me, it seems like it's easier to check the constraints about the amount of flow on each edge, so I'm going to do those first. Okay, so 9 out of 10, that's good. 2 over 10, 1 out of 10, 0 out of 5, those are all good. Those all comply with the capacity. 3 out of 3, 1 out of 1, 2 out of 2, 4 out of 9, 1 out of 5, 1 out of 1, 0 out of 1, 0 out of 3, 2 out of 7. Uh-oh, what's this? So this edge here from V5 to V8 has 5 units of flow over it, but it only has capacity 4. That is absolutely not allowed, so the constraints aren't obeyed. Once I find one violation of the constraints, it's sufficient to say that this flow was not feasible. Okay, so the flow along edge V5, V8 is 5, which exceeds the capacity of that edge, so this isn't a feasible flow. Is this a feasible flow? All right, let's do it again. So 9 over 10, 2 out of 10, 0 out of 10, 0 out of 5, 3 out of 3, 1 out of 1, 2 out of 2, 4 out of 9, 0 out of 5, 1 out of 1, 0 out of 1, 0 out of 3, 1 out of 7, 4 out of 4, 0 out of 5, 1 out of 4, 10 out of 10, 4 out of 10, 12 out of 20, 0 out of 10, 10 out of 10, and 5 out of 20. Okay, so it looks as if the flow value along each edge complies with the necessary constraints. So the flow value along each edge is greater than or equal to 0 and less than or equal to the capacity of that edge. Now I have to check the conservation of flow constraints, and this can be even more tedious and error-prone, so we just have to grind through it. Feel free to fast forward through this part, but you should be able to evaluate these constraints. Okay, so the conservation of flow constraints do not apply at vertex S and vertex T. They are the only vertices allowed to have shortages and surpluses. All right, so for vertex V1, total of 9 units enter, and I can see 2 plus 4 plus 3 is 9 units leave. So vertex V1 complies with conservation of flow. For vertex V2, 3 units enter, so I've got plus 3, and then I notice that 3 units leave, so vertex V2 complies with conservation of flow. Vertex V3 has 1 unit entering and 1 unit leaving, so that's plus 1, minus 1, so flow is conserved at V3. In V4, 2 units enter, and then, looks like only 1 unit leaves. So V4, there are other ways for flow to leave V4, but for some reason this assignment hasn't actually conserved flow at V4. So only 1 unit leaves when 2 units enter, which means conservation of flow does not hold at vertex V4, which means that the flow is not feasible. So because flow is not conserved at V4, the flow is not feasible. Okay, so that was a bit tedious to figure that out, but we were able to find the issue with the flow. What about this flow? Is this a feasible flow? Okay, here we go again. So 9 out of 10, 2 out of 10, 3 out of 10, 0 out of 5, 3 out of 3, 1 out of 1, 2 out of 2, 4 out of 9, 3 out of 5, 1 out of 1, 0 out of 1, 3 out of 3, 2 out of 7, 4 out of 4, 0 out of 5, 4 out of 4, 10 out of 10, 4 out of 10, 12 out of 20, 0 out of 10, 10 out of 10, and 8 out of 20. Great. Okay, so on every single edge, the flow does not exceed the capacity. Now let's go through and assess conservation of flow. So 9 units come into V1 and 9 units leave, so that's plus 9 minus 9, so flow is conserved. 3 units enter V2 and 3 units leave, so flow is conserved there. In V3, this is a different flow than the previous one. For V3, I'm noticing that actually 4 units are entering V3, but 4 units are leaving, so it looks like flow is conserved at V3. For V4, the problem we saw in the last example has been fixed, so 2 units enter and 2 units leave, so at V4, flow is conserved. V5 seems to have 7 units entering, and I notice that there are 7 units leaving, so everything looks good at V5. At V6, I have 4 units entering and 4 units leaving, so at V6, everything looks good. I think we're more than halfway there. At V7, I can see, let's see, so 2 plus 10 is 12 units entering and 12 units leaving along that edge there. So flow is conserved at V7. At V8, I see there's 4 units coming in, there's 10 units coming in, so that's a total of 14 units coming in, and I've got 14 units leaving, so flow is conserved at V8. Okay, one more to do. At V9, I can see 8 units coming in and 8 units leaving, so flow is conserved at V9, and that's all I have to check. Well, just that. So if you actually were able to stay with the video for that entire example, then congratulations. You have more patience for this sort of thing than I do. I was only barely able to make it through that, knowing that I'm being recorded. Prepare yourself to have to test these conditions on an exam question. In general, it probably takes a lot less time to do it by yourself on an exam than it took me to read out every number, because human brains are pretty good at being able to eyeball some things. That is, for many of these vertices, it's pretty clear that flow is conserved without having to fully add everything up. And so what I have here is a feasible flow because all constraints are satisfied. Now, in a feasible flow, it is always going to be true that the net flow leaving the source vertex will equal the net flow arriving at the sink vertex. So this isn't necessarily true if the flow is not feasible. Let's just verify that holds here. So basically what we can now do is reframe the formula for the value of a flow in the case where the flow is feasible only to be both of these two things. They are guaranteed to be equal. This expression here is the net amount of flow leaving the source vertex. If we go compute that, we can see, okay, there are 9 units leaving here, there are 3 units leaving here, that's 12, and then subtract off the 2 units that are coming back in. So that would be 12 minus 2, and so the value of f is equal to 10. And as I said, our standard definition is this left-hand side here. It's this equation. So the total amount of flow leaving vertex S is 10. So 10 units leave it. The value of the flow is just 10, not negative, just positive 10. Now the question is, what is the net amount entering vertex T? Okay, so 12 units enter vertex T here. 8 units enter vertex T here, so that's a total of 20 units entering vertex T. But then 10 units leave again, which is sort of bizarre, but I guess that's allowed, so 10 units leave, which means the total amount of flow arriving at vertex T is also 10. And because the flow is feasible, we actually know in advance that these two numbers are going to be equal. The amount leaving S will arrive at T, because it has to. Because where would the flow go otherwise? In a feasible flow where all constraints are satisfied, it's impossible for flow to end up staying at one of the intermediate vertices, or for flow to suddenly come into existence at an intermediate vertex, because we know that conservation of flow is satisfied. Therefore, all the flow that leaves vertex S must eventually make its way to vertex T. That finally brings us to the problem that we actually want to solve. So I've just defined what it meant for something to be a flow. A flow is, or in general, a flow is an assignment of flow values to edges. A feasible flow is a particular flow that meets those two constraints for all cases. So where the flow along each edge is less than or equal to the capacity, and for every vertex, conservation of flow is satisfied. But I want a particular flow. I would like a flow with the largest possible value. I want to get the largest possible amount of flow all the way from vertex S to vertex T. And we call that thing a maximum flow. So a maximum flow is a feasible flow with the largest possible value. Now there could be multiple flows that have this property. So there could be multiple ways. Suppose the maximum amount is 100. There could be multiple ways for me to get 100 units of flow from vertex S to vertex T. When I want a maximum flow, I just want one of those ways of doing it. And that's our task. Find a maximum flow for this flow network here. So the question is, how can we design an algorithm that does this? And I've already used the word feasible, and that might give you a hint as to the approach that I sort of want to take. I've tried this the other times we've tried to tackle an optimization problem recently, so for minimum weight spanning trees or minimum cost paths, I've mentioned that I really like this methodology where we start from some solution that meets our constraints but isn't perfect, and then incrementally work our way up through better and better solutions, ideally until we get to a point where we sort of get stuck. And maybe then we can conclude that no better solution exists and that that's the maximum, the optimal solution that we're looking for. Deep down, the reason that I like this technique is that it reminds me of techniques out of linear programming, which is just something that I like. Although I will observe that many of the problems we have solved, including minimum weight spanning trees and minimum cost paths, actually are basically linear optimization problems. They actually are examples of techniques or of problems that I could solve using linear programming. And it turns out that the maximum flow problem is as well. And as far as I know, so looking at other sources and talking to people, I think it's the case that of all the different optimization problems over graphs that people tend to learn about in algorithms courses, the one that is most closely associated with linear programming is this one, the maximum flow problem, to the point that you often cover maximum flow problems in linear programming courses because of how closely related it is to other important linear programming applications. So what I want to do is basically use the same technique I used to initially approach the minimum cost path problem. I want to start from some feasible flow, even if it's a flow that I know is not maximum, and then work my way up. And the reason for that, I guess, is that if I have a feasible flow at each step, I don't have to worry about bringing the constraints back into line. If I know that I always have a feasible flow, all I need to do is look for a way of increasing its value, not necessarily worrying about the constraints being violated and how I might fix them. Another reason why I like this technique is that if I start from a feasible flow and I take a series of steps that improves it, maybe each step can be small. I don't have to do very much work at each step, and maybe that makes it easier. The other thing is finding a feasible flow seems very easy. If you think about it, the constraints that we stated are obviously satisfied for this flow here. This is the flow with all zeros. So there is no flow along any edge. And if you think about the constraints we have to satisfy, so for example, that the flow along each edge is less than or equal to the capacity, that is obviously going to be satisfied for an all-zero flow because our definition of the capacity function required it to be non-negative. So even if the capacity were zero, the zero flow would satisfy that constraint. Additionally, it's very easy to make sure that flow is conserved if you're not pushing any flow through the graph at all. So obviously at vertex v0, there can't be a surplus or shortage with the all-zero flow because there's no flow to begin with. So it's pretty easy to show that the all-zero flow is feasible. So my idea, I guess, is starting from an all-zero flow, let's just see if we can push flow through the network in such a way that we maintain all of the constraints until we get stuck, until we can't push anymore. And then hopefully once we reach that point, we can show that there's no way we could have pushed anymore, and therefore that we have a maximum flow. Now, the technique I want to use is similar to what we tried earlier. What I'm going to do is start at vertex S. I'm going to find some path from vertex S to vertex T. Now, one obvious path might be this upper route here. I know in advance that when I try one on the slides in a minute, the slides are going to have a much fancier idea of a path to choose because the slides want to show off. But here's an example of a path from vertex S to vertex T. What I'll do is I'll find such a path, and then I'll work out how much flow can I push along this path. In this case, I think the answer is 2. Because notice that every edge along the path has capacity at least 2 remaining. So they all have currently 0 flow on them. So I could just add 2 across each of these edges. And what do you know? By the end of that, I'm now able to get 2 units of flow all the way to vertex T. Now, the reason why I want to do this with paths is that if you think about it, it's pretty easy to show that all of the constraints are satisfied if I push flow all the way from S to T in one step. I use an entire path. Because the constraints I care about are the constraint on capacities, which I am going to satisfy because I was very careful to not choose an amount larger than the capacity of any edge, and the conservation constraints. But it's easy to show that the conservation constraints will be satisfied after this modification, because if I push 2 units all the way from vertex S to vertex T, then any vertex that those 2 units pass through isn't going to violate conservation, because the 2 units are going to go into the vertex, and the same 2 units are going to leave the vertex. So if I use paths like this, I think it's pretty easy to show that if I start from a feasible flow, and I'm careful about how many units I choose to push through the path, that the constraints will be satisfied when I'm done. So as I mentioned, the slides, of course, want to try some fancier looking path to show off, so here it is. So suppose I start at vertex S, and I wander down to V3, then to V5, then to V8, then to V9, and then to T. If I look at that path, so suppose I look at that path without actually adding any flow along it yet, so I go all the way to V3, then I go up to V5, I go across to V8, I go down to V9, and then I go up to T. And the question is, how many units of flow can I push along this path right now? Because I obviously want to push as many as I possibly can. Well, I could push up to 10 here, but it turns out that I can only push 5 here and 4 here and 10 here. Well, the bottleneck is pretty clearly this edge. This edge has a lower available capacity than anything else on my path. So I'll choose to push 4 units along every edge on the path, and I end up with this configuration here. So generally in these slides, when you see one of these paths in green, if you see these numbers next to it, that means that the current state of the flow includes that update. So when you see a +4 here, that means that this number has already been updated with 4 extra units of flow. That's why I had to scroll back by 1 to show what the graph looked like before that change. Notice that after I've done that, after I've added those 4 units of flow, sure enough, T is receiving 4 units, you can verify that the constraints are satisfied, that I do have a feasible flow, but notice that this edge is now saturated because one of the edges along my path is going to be a bottleneck, maybe more than one, but in this case it was just this one edge. It makes sense to send the maximum possible amount of flow I can for every path that I choose, and it also makes sense logically that doing so will result in at least one edge along the path becoming fully saturated. And once it's saturated, I can't push any more flow along it ever again. Which means if I go looking for another path to send flow along, this edge will never participate again because this edge is already full. I can't put any more along it. We're going to call this type of path an augmenting path. So an augmenting path is some path from S to T that has available capacity. So if I look at the graph in its current state, this path here is an augmenting path because it is possible to send at least 1 unit of flow all the way along the path, respecting edge capacities, and have it reach vertex T. Now, it actually turns out this definition is not correct. It turns out we're going to need to modify it later to attend to one very important other case. We'll just start from this definition and work our way up. So an augmenting path is some path P where the first vertex on the path is S and the last vertex on the path is T, and for every edge along the path, the current amount of flow on that edge is less than the capacity of that edge. In other words, there is still some capacity available along that edge to use. So if I go looking, I can think of an augmenting path on this graph that involves edges I've already tried. So I could go along S, from S down to V3, and then across to V6, and then across to V9, and then up to T. I think I can push 1 unit of flow along this augmenting path. So I would increment the amount of flow on this part, and here, and this edge would become saturated. Now I know the slides are eventually going to want to try that path, but I don't know when they do that. I think they want to try some more fancy business in the meantime. I'm going to need to change the definition of augmenting path in a while, in about 30 slides. There is an important case that I'm missing, so do not use this simple definition as your standard go-to definition of augmenting path. It's just a step along the way. Okay, so at this point, I've got the value of my flow is 4. I'm getting 4 units all the way to vertex T, but only one edge is fully saturated. So I'm going to draw that edge in gray to indicate that although it's important that there are 4 units along that edge is never going to help me again as far as crossing the edge in this direction to look for new ways of pushing flow, because I can't send any more flow from V5 to V8 because the edge is now full. The reason why saturated edges are useful to look at, why it's helpful to gray them out, is in my opinion, if there aren't very many saturated edges in the graph, that does seem to mean it's likely that I should be able to get more flow to T. As edges fill up, so if I notice that all of these edges are full, then it does seem like maybe it's going to be hard to get any more flow to T because a lot of routes are blocked. In a sense, once an edge becomes saturated, it's sort of like it ceases to exist. And once enough edges cease to exist, I suppose that then I might be done. Then I might be stuck. But right now, only one edge is saturated, so I should go looking for more augmenting paths. So sure enough, the slides are trying some fancy business. So another unit of flow can be routed along the path from S all the way up to T here. And I just go via this sort of zigzag path. Notice that when I do that, this edge becomes saturated. So if I look at all of the edges on this path, the one with the lowest available capacity is this one, and it becomes saturated. And now T is receiving 5 units of flow. I can then choose this path to route 2 more units of flow. Notice that when I choose this path, this edge becomes saturated. Now in this case, I was pushing 2 units along this particular path, and this edge becomes saturated at 3 because at the end of the previous step, this edge ended up with 1 unit flowing across it. So when I add those extra 2 units, I end up saturating the edge. Now as far as how I knew that I was supposed to use 2 edges, if I look at the graph at the end of the previous step, so that would be this step here. If I look at the graph at the end of this step and I look at my next augmenting path, so I can find a path that gets me from S to T along edges with available capacity. It would be, I think it was this one here. And then I look at the available capacity of each edge. Okay, so there's 9 capacity available there. There's obviously 9 capacity available here. There's only 2 capacity available here. And then there's 3 available here and 15 available here. So this is the bottleneck, so I push 2 units. And that results in this edge becoming saturated. Okay, then I try this augmenting path here, bringing my total to 8, and that saturates this edge. And in general, each of these paths I'm choosing is guaranteed to saturate at least one edge, because otherwise I should have been pushing more flow through the path when I did. And then finally, I do this one here. I think there might be one more. Oh no, wait, not yet. So at this point, I've got the value of my flow is 9. And what we'll notice at this point is actually I get stuck. If I go looking for a way to get from vertex S to vertex T, traveling only along edges that have available capacity, that's how I could find an augmenting path, I'm going to get stuck. So I could actually even do a traversal to verify this. Let's try reaching vertex T from vertex S using, let's say, a BFS tree. Okay, so I'll use BFS to go up to vertex V1. I can go down to vertex V3. I'm only going to travel along edges that have available capacity because these ones basically don't exist to me as far as I'm concerned right now, looking for an augmenting path. I go from V1 down to V5 and down to V2, and that's it. I can't go anywhere else from V1 because I can't use this saturated edge. I can't go anywhere from V5 because I can't use this saturated edge or this saturated edge. I can't go anywhere from V2 because the only destinations are places I've already been, like V3 and S. And I can't go anywhere from V3 because my options are either to go up to V5, where I've already been, or to go across to V6 on this saturated edge. So there is no path from S to T that uses only edges that have available capacity. But what does that mean? If I delete the saturated edges, hopefully it's even more clear what's going on here. So notice how if I delete those saturated edges, which I'm not allowed to use, the graph has sort of become segmented into 2 pieces. There's the piece containing S and the piece containing T, and you can't get to the piece containing T from the piece containing S. You can get back, but that's not helpful to me. I want to get flow from S to T. So the question is this a maximum flow? And I'll spoil it and say that I can't actually answer that question just yet. And it's strange because this is a pretty fundamental question for this problem, but I won't be able to definitively answer that question, to know what a maximum flow truly is, until the beginning of the next lecture. About 3/4 of the way through this lecture, we will see some glimmer of what it means for something to be a maximum flow, of conditions that could occur to know that a flow is maximum. I'm also going to spoil that, in fact, this isn't a maximum flow. It seems like it is because the procedure I was trying has sort of capped out. I can't go any further. I can't find any more augmenting paths. But that might just be because of bad luck. It might be because I didn't choose the right augmenting paths to begin with, or maybe because I need to open my mind a little bit to other ways of pushing flow between vertices. So it turns out that the answer is no, it's not a maximum flow, and that although no augmenting path appears to be available, there is a way of getting at least one more unit of flow to vertex T. I can show off how to do that. So here is our previous attempt at a maximum flow. This is the point we got stuck. Let's try deleting all of the flow on this edge here. Okay, so if I do that, we actually have a problem. So if I'm no longer sending 1 unit of flow from vertex V4 to vertex V5, well, that means that V4 now has a surplus, and V5 now has a shortage, because that unit of flow is balancing the conservation of flow constraint at both vertices. Okay, but bear with me for a minute. So I've just deleted the flow across the edge V4, V5, and I've created a problem with my constraints. What I want to illustrate is I can fix that problem. So if I want to get rid of the shortage at V5, all I have to do is find some way of routing 1 unit of flow from S to V5. And that's easily doable. There are plenty of ways to get to V5. A minute ago when I was trying my BFS traversal, I observed that it was possible to still send flow from S to V5. Okay, so I send 1 unit of flow from S to V5. That gets rid of the shortage there. Now the question is, what do I do with this surplus? All I really have to do is to route it onwards to T, and that's pretty easy too. There's a pretty clear path from V4 to T. Okay, so I do that. Notice that once I've done that, 10 units of flow are arriving at vertex T. And if I go and check the constraints, all of them are still satisfied. This is now a fully feasible flow that does have a value 1 greater than my previous attempt. So what happened? Well, I suppose you could argue that because of whatever augmenting path chose this vertex, I created some kind of a bottleneck in my graph that resulted in it being impossible for me to route as much flow as I wanted. Maybe with a different sequence of augmenting paths, I could have arrived at this flow without having to make the adjustment that I made a minute ago. So here I have a feasible flow with a value 10. Now the question again is this it? Is this the maximum flow? And the answer again is, well, now that we know that it's not as obvious as it seems. So the previous case where we had value 9, I don't know, I wouldn't blame you for being sort of confident that we had found a maximum flow. It did look as if there was no option as far as pushing more flow through the graph. And yet I was able to find a way of doing that. So can I do that here? Well, it makes sense to not have too much confidence that I could or couldn't, because maybe there are more details hiding in the background. It turns out that the answer is that this is a maximum flow, but how do we know that? So before we address that aspect, I want to talk a bit more about that adjustment that I just did. So the adjustment that I did a minute ago was I just chose an edge, apparently at random. Like, how did I know this edge was the problem? I chose this edge, deleted the flow across it, and then fixed the problem that created. So, I mean, I could certainly imagine a case where an algorithm could be designed that does that, but how do I know which edge to pick? And how do I know whether picking a particular edge will yield any meaningful results? I'm going to approach this in several ways because, as far as I can remember, when I learned about maximum flows, this particular aspect really annoyed me. There was just something about it that made the problem a great deal more complicated. So the next thing I'm going to do, which does have a pretty counterintuitive outcome, I'm going to describe it in a few different ways. Okay, let's rewind to the state of the flow before that adjustment. So here I've got 9 units of flow arriving at vertex T again. And again, I have that 1 unit of flow traveling across the edge V4, V5. So I know this isn't a maximum flow. The question I'm really trying to get at here is, how can I formalize the process of fixing it? So a minute ago, I was able to fix it and get us to a flow of value 10. I want to make that something formal. I want to make it something an algorithm can do and not just me randomly choosing an edge and being lucky. So if I only travel along edges in the correct direction, so if I start at vertex S and I walk along edges with available capacity in the right direction, there is no way to reach vertex T, unless I take a saturated edge, but it makes sense that I'm not allowed to do that. I can't push 3 units of flow across this edge in any case. So if I ignore the saturated edges and I walk along edges in the correct direction, there are no augmenting paths. Now, as I said a minute ago, maybe the solution to our problem is just to open our minds a bit. Maybe I need to just define augmenting paths a little bit differently. So there is no way of finding an augmenting path if I have to walk along edges in the right direction. So what do I do? Well, I don't know. If the rules don't work for me, then maybe I should try and change the rules. Why don't I try walking along edges in the wrong direction? Now, this doesn't sound like a good idea. I mean, I understand. Like, the whole point of having directions in a directed graph, I mean, nobody's been saying that more than I have for the last 20 lectures. If we have a directed graph with edges that have a particular direction, we should be respecting the direction. And now the minute that becomes inconvenient for me, I'm like, yeah, don't worry about it. Let's go in the wrong direction. But bear with me. Suppose that we decide to push 1 unit of flow from vertex S to V5. Now, doing this obviously creates a surplus, because in general, if I push flow along a path that does not end at T, then wherever the path does end is going to have too much flow. Okay, so I've done that. I've pushed 1 extra unit to vertex V5. I clearly have to remedy this before I can call my flow feasible again. So how do I do that? Well, what I observe is the problem is simply that too many units of flow are getting to V5. How can I get around this problem? Suppose I've already created the surplus, that's already been baked in. How could I solve the problem? Well, there are 2 ways of getting around it. One is that I could send this 1 unit of flow onwards somewhere. But you'll observe that there are no outbound edges of V5 that I can use. They're all saturated. I can't send anything here. I can't send anything here. And although I did just suggest breaking the rules in one sense, I do not want to break the rule about the edge capacities. I do not want to try and send 5 units across an edge. Okay, so there are 2 ways of getting rid of this surplus. Either I send the surplus away. Okay, that's one option, but it's not going to work. Or I resolve the surplus by basically doing return to sender. I could say, hey, don't send me that extra 1 unit. So I could send it back to vertex S. I could go back to the previous step. That's one way of doing return to sender, but is it the only way? Really, I could just say to anybody sending flow to vertex V5, hey, don't send me 1 more unit of flow. So I could say, hey, V3, I don't want your 1 unit of flow. That's one option. But I could also say that to V4. I could tell V4 to take back this 1 unit of flow. If I do that, the surplus at V5 will go away. If I can remove 1 incoming unit of flow from V5, the surplus disappears. So one option would be to tell V4, hey, take your 1 unit of flow back. Now this means the surplus at V5 disappears, but really it just gets moved over to vertex V4. But we saw earlier that if I have a surplus at vertex V4, that's easy to remedy. I just push it onwards to vertex T. Okay, so I do that. So since V4, V5, this edge here, previously had 1 unit of flow, choosing not to send it, if I tell V4, hey, I don't want your 1 unit of flow, semantically that's equivalent to sending -1 units of flow from V5 to V4. I'm basically doing a return to sender operation. Okay, this is just getting stranger and stranger. So a minute ago, I'm like, try pushing flow in the wrong direction. And now I'm talking about sending negative flow in the opposite direction. I'm not sure that I can convince you that this is a rational strategy, but if I can't convince you, maybe my friend Benjamin Franklin might be able to convince you. Because all I'm really saying here is that if I have extra that I can't use, one way of getting rid of it is to proactively send it somewhere. Another way of getting rid of it is just to make sure that other people aren't sending me as much stuff. So when I say something like send -k units or -1 units from vertex V5 to V4, really if I turn that around, what I'm actually saying is tell vertex V4 to send 1 fewer unit of flow. So V4 ends up with that surplus, which I can then resolve by walking all the way over to T. All right, so there's a lot of ways we can contextualize this. I could think of the sending this 1 unit as return to sender. I can think of it as a penny saved is a penny earned. But the idea is what I'm really doing is finding some way of negotiating through following this edge essentially backwards. If 1 unit of flow is being sent to me, then I have the option of simply sending it back. I can just say, don't send it to begin with. And it does feel like I'm sending -1 units, but really I'm just saying don't send it to begin with. And because it's not sent to begin with, then there's 1 extra unit available at the destination, just as if I had pushed 1 unit of flow in this direction. In other words, I could maybe redefine augmenting paths to allow that operation. If there is an incoming edge that has flow available, I could use the return to sender methodology to just keep walking along my path and get a little bit closer to my destination. And then I can go all the way through. So once I move the surplus to V4, I can complete the path, get to vertex T with a value of 10. So I can push that 1 unit onwards. Now, after describing it in several different ways and bringing Benjamin Franklin into the equation, I'm not sure if it still makes that much sense, even if you see my side of the story. But I think I now have enough tools to represent the actual operation I'm performing in terms of finding an augmenting path. So I'm going to return again to the state of my flow before the adjustment. So we're back at the state where T was receiving 9 units of flow. So if I take this path here, I go from S to V3, I go from V3 to V5, and then I go backwards along the edge V5, V4, and then I move on to V7 and then T. I can call this whole thing one path. It only really has one weird exceptional case, which is that in the middle, it's working backwards along an edge. Now the edge it's working backwards along is special because the edge actually has flow in the opposite direction. All I'm really doing is pushing that flow backwards along that edge. But it has the same effect as if I had moved flow forwards along an edge in the opposite direction. Okay, so as I said earlier, the flow we end up with after following this special-looking augmenting path, pushing 1 unit of flow along it, is actually a maximum flow, although we're still not ready to show why that is. I can say that, and it sort of looks like that might be the case, and there are no surprises hiding in the background, but we don't have the theoretical tools yet to be able to assert that this is definitely maximum. We're going to get there, but actually it turns out that to prove the theorem that we need, we first need to develop an algorithm, which is sort of circular, because how do you develop an algorithm to find something that you can't yet classify? Unfortunately, this is just one epic case of bear with me, this whole topic. Before I go on, though, I guess I have to modify my definitions to account for this weird mechanic I just introduced of being able to walk backwards along edges. And I believe that once I'm done ironing out this terminology, I think you'll see what I meant by it. I think once I have these new notational bits in place, it'll be pretty clear what I was really doing. Okay, so I'm going to define something called the residual capacity, which is one way of generalizing the idea, and we're already doing this. If I have two vertices u and v, so there they are, and I want to find an augmenting path that goes through vertex u to vertex v. Suppose we find that there are currently 5 out of 7 units being pushed from u to v. If I use an augmenting path that goes through vertex u to vertex v, then that augmenting path could push at most 2 units from u to v, because there are already 5 units being transported and the capacity is 7. I'm going to define this thing called the residual capacity to indicate how much capacity is left from vertex u to vertex v. So let G be a network and let F be a particular flow, because the residual capacity depends on the current state of the flow. I'm going to define the residual capacity CF of uv, so the F there is to denote that it's with respect to the particular choice of flow F, to be, well, it's in 2 terms. I'm going to start with the term on the left. So the left term of the expansion is take the current capacity and subtract off the current flow. So 7 minus 5 is equal to 2. So in this example, the residual capacity of the edge uv is 2. Now there's this other case that I have to account for, though, which is what if I want to send flow backwards, which is weird, but is actually allowed, and it only happens if flow is already being sent in the opposite direction. So suppose that I have a flow that looks like this. I've got flow already traveling, let's say 5 out of 7 units are already traveling from V to U. I have the option of having vertex U tell vertex V that those 5 units should be returned to sender. I don't have to send all 5 of them back. I could also send only 3 of them back, but I can use this as a way of basically sending 5 units from U to V. So in this case, the residual capacity, the capacity available to go from vertex U to vertex V, is actually going to be equal to 5, because I could just send back those 5 units. And that's going to correspond to the right term in this expansion. So in this case, the residual capacity is 5. Because I can do a return to sender operation on 5 units of flow coming to vertex U from vertex V, and that functions basically as the same operation as sending flow from U to V, because if 5 units of flow end up in vertex U, and I send back the 5 units that V has sent me, then vertex U doesn't have a surplus, and vertex V does, exactly as if I had sent the flow across an edge UV. Okay, so in this case, the residual capacity is 5. Okay, but there is a case where both are operational at once. Just a minute while I redraw my diagram a bit here. So what if there is an edge from U to V and an edge from V to U? This is allowed. Suppose that the current residual capacity along the edge from U to V is 3. So there are 2 out of 5 units of flow traveling from U to V. But also that on the edge from V to U, let's do 6 out of 10. So there are 6 units of flow being sent from V to U and 2 units of flow being sent from U to V, which is sort of ridiculous. Like, it's unclear why I'd ever have that case. In fact, actually, let's modify that. Although such a case could theoretically occur, it may not occur in any of the cases we're going to look at with the algorithms we're going to use. So suppose you have this much more realistic situation here. There is an edge from U to V that has capacity 5, and it's currently empty. But additionally, vertex V is sending me 6 units of flow. The question is, if I want to send flow from U to V, what is the maximum amount I can send right now? And the answer is, well, I could send 5 units via this edge, and I can send back these 6 units. So the answer is actually 11. And I compute that with my formula for residual capacity by taking the capacity of the edge UV, that's 5, subtracting off the flow from U to V, that's 0, and then adding the flow in the reverse direction. That would be 11. Okay, so the residual capacity of some pair of vertices UV is the total amount of flow that I am able to send from U to V right now, via any means, either sending it backwards or sending it forwards. And as before, just like how I defined the capacity of a non-existent edge to automatically be 0, I'm using that property here, and it really helps the definition. Otherwise, I would need multiple cases to account for which edges exist and which edges don't. So there's residual capacity. I'm going to use that to redefine augmenting paths, to formally allow an augmenting path to contain the return to sender case. So an augmenting path, and this is the real definition of an augmenting path. An augmenting path is a sequence P of vertices Q1 up to Qk, where Q1 is the source vertex S and Qk is the sink vertex T, such that for every pair of vertices, every pair of consecutive vertices along the path, the residual capacity between those two vertices is greater than 0. So there is some flow that can be pushed from vertex Qi to vertex Qi plus 1. Okay, so the next question is, suppose I find such an augmenting path. Let's just quickly draw, let's draw a quick example of an augmenting path here. So suppose here's my source vertex S, here's V1, and then we'll have to add a sort of that quirk in the middle there. There's V2, and then there's my vertex, my sink vertex T. And we'll draw in some capacities here. Let's suppose that this edge currently has 2 out of 5. I'm sending 3 out of 10 units backwards from V2 to V1. And then finally, I've got 0 out of 7 units available, 0 units of flow across the edge V2 to T. So what we realize is that if I choose this augmenting path from S to T, pretty much the next question I have is, how much flow can I send along this augmenting path? And the answer is going to be, it's whatever the minimum capacity of one of the edges in the path is, the minimum residual capacity. And actually, I've just realized that my example isn't great for that, so I'm going to change this to be 4 out of 5. Okay, so the residual capacity between S and V1 is 1. I can send up to 1 unit from S to V1. The residual capacity from V1 to V2, well, in this case, I could send up to 3 units backwards from V1 to V2, so the residual capacity is 3. And the residual capacity from V2 to T, in this case, is just 7, because the whole edge is the edge currently has no flow on it at all. So how much flow can I push along the path? Well, the answer is 1 unit, because of course I'm constrained by whichever edge is the bottleneck, and in this case it's this edge here. So because I often want to know this information, what is the maximum amount of flow I can push across a particular augmenting path P, I'm going to define that as its own special case of residual capacity. So define the capacity of an augmenting path, which I'm going to denote by this notation here, to simply be the minimum residual capacity of any pair of consecutive vertices along the path. So if this is my path P here, then the residual capacity of P is 1 in this case. All right, one more definition. I want to define a special secondary network that helps me visualize residual capacities. I may choose to use this network in my algorithm, or maybe I won't. There are ways of implementing the algorithm we're about to describe that doesn't require me to construct this thing, but certainly looking at this thing can really help clear stuff up. Okay, so you give me a particular flow network G, you give me a particular flow F. I'm going to define something called the residual network. I'm going to call it G of F. It's going to have all the same vertices as G, including the same source vertex and sink vertex, but it's got a special edge set. The edges of GF, the residual network, correspond to all pairs of vertices which have a positive residual capacity in G. And this could include vertices, pairs of vertices, for which there is no edge UV in G. So notice how none of this is predicated on the actual edge set of G, just on the residual capacities. Now, additionally, because this thing GF is a flow network, I have to define the capacity of each edge. I'm going to define the capacity of each edge just to be the residual capacity. So the edge exists if its residual capacity in G is greater than 0, and the capacity of that edge in GF is the residual capacity in G. Let's take a look at one of those things. So here is a flow network G, and you'll notice I've already put some flow into the network just to illustrate what happens in the residual network. Over on the right, I have the residual network. Now, let's take a look at this edge here, the edge V4 to T. The residual capacity from V4 to T is currently 10. Notice that in GF, there is an edge from V4 to T with capacity 10. That shouldn't be too interesting because it's the same edge in both cases. Okay, fair enough. Let's take a look at, let's try this edge here, the edge V5, V2. So in the graph G, in the current state of the network G, the residual capacity from V2 to V5 is 1. I can currently push up to 1 more unit of flow from V2 to V5. Notice that over here in my residual network, the edge from V2 to V5 has capacity 1. But also notice that there's a new edge. There's an edge in the opposite direction. What if I ask about the residual capacity from V5 to V2 in my network G? Well, if I wanted to, I could send up to 2 units backwards along the edge V2, V5. I could return those to sender, which means the residual capacity is 2. And notice that in my residual network, there is now an edge from V5 to V2 with capacity 2 to indicate that I have the option of sending flow from V5 to V2. What's great about the residual network is if I want to assess whether I can send flow from S to T, all I really have to do is find any path in the residual network. So for example, here is a path in the residual network. And this tells me there is some way of sending flow from vertex S to vertex T in the original network. It might require traversing some edges backwards, but some way does exist. And then finally, let's take a look at this saturated edge here. So currently, the residual capacity from V1 to V3 is equal to 0. There is no way of sending flow from V1 to V3 because edge V1, V3 is saturated. And notice that there is no edge from V1 to V3 in the residual network. On the other hand, there is an edge from V3 to V1. But that doesn't surprise us too much because if I look at the residual capacity of V3, V1, it is actually equal to 5. And sure enough, there is this edge with capacity 5. So the residual network gives me a way of sort of sifting through all of these issues of going in forwards direction or reverse direction over a particular edge. So the capacity of each edge in the residual network is the total amount of flow that can be moved from vertex U to vertex V via any means, whether it's via taking an edge in reverse, via the return to sender procedure, or whether it's just pushing flow in the normal forward direction. If I set all edge flows to 0, well then the residual capacity of every edge is equal to its regular capacity, and so the residual network is exactly the same as the original network. When I add flow to my original network, the capacities in the residual network change. Now in these visualizations, if you see an augmenting path with an augmentation on the left, the thing on the right, the residual network on the right, is the state of the residual network after that augmentation. So we'll notice with the all zero flow, if I look at the augmenting path I'm going to use here, so this sort of zigzagging path, notice that I can get all the way from S to T in my residual network via this route here. If I look at the capacity of the edges along the way, the bottleneck is pretty obviously the edge V3, V4. That's telling me that if I chose that particular path, the amount of flow I'd be pushing is 1 unit. If I perform that augmentation, sure enough, I push 1 unit from S to T. If I now go look at my residual network, notice that because the edge V3, V4 became saturated, it no longer exists in the residual network. Now there's an edge V4, V3, indicating that if I want to, I can push flow in reverse from vertex V4 to vertex V3. And so additionally, because I routed 1 unit of flow from V1 to V3, a new edge shows up from V3 to V1, reflecting my new ability to send flow backwards to return this 1 unit of flow from V3 to V1. And in general, if I find any directed path in my residual network, that will correspond to some augmenting path in my original network. So if I look at this zigzag path here, if I go back to the step before that, so I can see this path in my residual network, this is a normal directed path from S to T. This corresponds to the augmenting path we see on the next slide, this one here, which does take all edges in the forward direction. Notice that once I saturate this edge and this edge, their orientation is flipped in the residual network because it's no longer possible to send flow from V3 to V5, but it is all of a sudden possible to send flow in the opposite direction. Okay, and so I add this augmenting path as well, I add this augmenting path as well, and then I augment along this path as well. Now at this point, after all those augmentations, I'm now sending 11 units from vertex S to vertex T. And notice that if I look at my original graph, there are no augmenting paths left that use only forward edges. That is, if I want to walk respecting edge directions along edges that are not full, I can get from S to V1, and I can get from S to V2, and I guess I can get all the way up to V5, but that's it. But the question is there a way still of augmenting the graph? Can I find an augmenting path that takes any edges in reverse? And the answer is I can actually easily figure that out just by looking at the residual network. I mean, I could stare at this until I found a way of traversing edges in reverse. Maybe that works for you. Your mileage may vary. Good luck if it does. But I can actually find an augmenting path pretty easily by just doing a regular traversal of my residual graph, of my residual network. So let's say I do a BFS traversal. I go from S to V1, and then I get stuck. There's nothing I can visit from V1 in the residual network. Okay, so I go from S up to V2. I go from V2 to V5, and there, look at that. there's an edge from V5 to V3. Now, we can see in the original network this corresponds to sending flow backwards. That's not my concern right now. I'm just looking for a path. Okay, and then I can climb from V3 up to T. Okay, so the path I found was this one. It went from S to V2, from V2 to V5, and then it went backwards along this edge to V3, and then forwards along the edge to T. Now the question is, okay, so how much flow can I push? If I go look at my residual network, well, I can do 5 units there, 3 units there, 2 units there, and 3 units there. So the bottleneck is this one. So it looks like I can perform an augmentation where I push 2 more units of flow along the routing that I've found. And that would be basically exhausting this. I would be sending all of the units of flow from V3 to V5. I'd be sending all of them back. Okay, so I'm performing, this is the augmenting path I found. Now the augmentation hasn't happened yet. You'll notice that the value is 11 here and it's still 11 here. The slides are actually catching up with what I just said. So because I can push flow backwards along the edge V3, V5, as evidenced by the fact that in my residual graph I was able to find a path to T, there is still an augmenting path available by my new, more comprehensive definition of an augmenting path. And in the residual network, the path that I found only requires forward edges. So if I'm uncomfortable by this strange idea of walking backwards along an edge, I don't have to worry about that if I go searching for paths in my residual network. All right, so I go perform the augmentation. I realize that I can perform an augmentation with 2 units of flow, so I push 2 extra units this way, 2 extra units this way. I then push -2 units in reverse, which means I subtract 2 units from this edge, the edge pointing in the opposite direction, bringing it down to 0, which is sort of the reverse equivalent of saturating it. And this is the edge. Along the various edges of the augmenting path that I found, this is the one that was the bottleneck. And so instead of saturating it, I'm setting it back down to 0. It can't go any lower than that. If it could, I would have been able to push more flow. And then I send the 2 units onwards to T, and I end up with a feasible flow that has value 13. Now let's stop at this point and see what we end up with. So notice how, if I look in my my original network, it still isn't possible to reach vertex T using only edges that I traverse in the forward direction. But that was a bit of a diversion anyway, because we noticed that in our residual network, the last time this happened, I was still able to find an augmenting path. But in this case, I can't. If I do a traversal starting at vertex S, I go over to V1 on this side, I go over to V2 on this side, I go up to V5, and that's it. There are no edges that I can traverse that take me out of this little cluster of vertices here. The only edges in the residual graph that interact with the cluster are the ones that point inward. There's no way to leave the cluster. But also notice that if I go looking at all of the edges leaving the cluster in the original network, they're all saturated. So I found a collection of vertices where for this flow here, the only bridges between this collection of vertices and the outside world, so S is inside the cluster, T is outside the cluster, which means that any path from S to T is going to have to leave the cluster at some point. But all of the edges leaving the cluster are saturated. All of the bridges between the cluster and the outside world are full. And you know what this tells me? It seems as if there's no way, even if I chose different augmenting paths or anything else, there is no way I could ever get a flow with value greater than 13. Because any augmenting path, no matter how I chose to found it, no matter which order I chose to process my augmenting paths, any augmenting path would need to pass through one of these edges. And all of these edges are saturated. There's no way to push any more flow along any of them. And so I think, to me, this looks like evidence that I do in fact have a maximum flow. So since any flow from S to T must eventually exit this cluster C along one of the highlighted edges, these are the only edges leaving the cluster, and the total capacity of these edges is 13 and all of them are saturated, the total value of any flow must be less than or equal to 13. Since I currently have a flow of value 13, that means it's maximum. I found maximum flow. So we now know that F is a maximum flow. But didn't I say that we wouldn't be able to prove whether a flow is maximum until the beginning of the next lecture? That still holds, because I'm going to argue that what we've done here is maybe just a little bit of luck at the moment. That is, because I was able to identify this particular cluster, and I was able to identify that the edges leaving the cluster are all saturated and have total capacity 13, by having all of that information, I was able to deduce that my flow was maximum. And it does turn out that the theorem we're going to prove in the next lecture actually uses the same logic logic. We just haven't nailed it down yet. We just aren't at a point yet where we can be guaranteed that we always have this condition, that we're always going to be able to find that all of the bridges between S and T are saturated, that there's no way of increasing the flow across those bridges, and therefore that the flow that we have is maximum. The cluster that we found, though, so this collection of vertices here, this cluster C, is an example of something called an ST cut, which we're going to talk about in the next lecture. This is a key ingredient in the big theorem we're going to prove. The theorem I'm talking about, the one that actually establishes for us what a maximum flow really is, in my opinion, is the most profound theorem of this course. That is, all of the work that we've done in algorithms up until this point, in some sense, has been leading us towards a theorem as profound as the one we're going to see at the beginning of the next lecture. So I'm really raising expectations here. It better be good. Now, I can't do that yet. We actually, as I mentioned, the proof of the theorem is going to require that we already have a particular algorithm. So we have this funny chicken and egg problem where I have to create an algorithm that I can't prove the correctness of because I can't prove the correctness until I know what a maximum flow is, but I don't know what the maximum flow is until I have the algorithm. And that's going to be a weird thing to resolve, but fortunately for me, I don't have to do that during this video. So for this lecture, I want to create an algorithm that I claim will find a maximum flow. We'll talk about its running time and then talk about a few assumptions and then wait until the next lecture to finally iron that situation out. So here's the algorithm. This is just the procedure we've already been using. So what I do is I'm going to start from an empty flow, so a flow where every edge has flow value 0. I'm going to go looking for an augmenting path. That would be any directed path in the residual network. As long as I find an augmenting path, I'm going to perform an augmentation. I'm just going to keep doing that until I get stuck. And I claim that this will find me, that the flow I eventually find at the end is a maximum flow. I'm going to use array-like notation to refer to the flow itself because normally if we define the flow as sort of a function, but because I'm modifying the flow values, it feels weird to do that, to write something like f of uv equals f of uv plus something. That just looks strange. So I'll use array-like notation because I'm probably storing the flow values in some kind of a table or associative map or something anyway. This technique, the thing I've drawn here is what I'm going to call the Ford-Fulkerson algorithm. There are some that call it the Ford-Fulkerson method. More on that in a minute. But fortunately for us, we're used to, by now, sort of getting on our guard the minute that I use an algorithm named after people, because you all know that I love going off on long tangents about how we name algorithms after people. But don't worry, you can heave a nice sigh of relief because it turns out there is no controversy here. Everybody calls it the Ford-Fulkerson algorithm. There's no need for a history lesson because it was published by these two people jointly. They published one paper with both of their names on it. So there's no need to go work out who invented what first. It's the Ford-Fulkerson algorithm invented by both of them, and they published it in 1956. Now you might recognize one of these names. Hey, there's Ford. This is actually the same Ford that we have in the Bellman-Ford algorithm. This is one, therefore, of many algorithms that we've seen in this course that stem from the Rand Corporation in the 1950s. Now, who knows why that is? Is that because a huge number of incredibly important algorithmic results came out of the Rand Corporation to the exclusion of everywhere else? Well, maybe. But it could also be that what we teach in algorithms courses is heavily based on what algorithms are found in algorithms textbooks. And what you find in an algorithms textbook in 2025 might just be based on what was in algorithms textbooks in 1975, which might just be based on what was in algorithms textbooks in 1965. Because the people writing today's algorithms textbooks probably learned about algorithms in the 70s or 80s or 90s, and they might well, when they sit down to write an algorithms book, think that the most important algorithms are the ones that were taught in their algorithms course. And I could be guilty of that as well. That is, the algorithms that I've been covering in this course, largely speaking, have been dictated sort of by larger curriculum decisions, that many of which are outside of my direct control. That is, I have influence in the curriculum process, but we live in a society and etc. and etc. But it could also be that I think certain algorithms are important because they're algorithms that I learned when I took an algorithms course. And in turn, those are algorithms that the instructor learned when they took an algorithms course. So I have no way of knowing whether truly the algorithms we've been talking about over the the last, I don't know, 37 lectures, whether all of them truly are as globally important as maybe they seem. Certainly, I think it's reasonable to say that merge sort is a fundamental and important algorithm. And I do not back down, and I will never back down from the claim that DFS and BFS, the fundamental traversals, are the most important algorithms in computer science. But who knows whether minimum weight spanning tree algorithms, in the grand scheme of things, are so important that they warranted their coveted position among the limited number of lectures in this course. So keep that in mind. I think that, however, it is true that network flows are significant enough that one way or another, whether it's the Ford-Fulkerson algorithm or something else, we would eventually have to learn an algorithm to solve problems like this. Okay, so we don't need a history lesson for why it's called the Ford-Fulkerson algorithm. It's just named after the people that invented it, and there's no controversy about that. But what's this business of calling it algorithm versus method? Okay, I'm going to talk about that. So there are people that claim that we shouldn't call this thing the Ford-Fulkerson algorithm, but we should just call it the Ford-Fulkerson method, because they say it's sort of ill-specified. So, for example, it says, while there is an augmenting path, perform an augmentation. But it doesn't give instructions for exactly how you should go find an augmenting path. And there are those that argue that this means it's not really an algorithm at all. It's sort of a broad framework for an algorithm. I don't really buy that argument. Now, there is a different argument that they sometimes make that I do sort of understand for why you might want to call it the Ford-Fulkerson method. I'll come back to that in a little while. But as far as the idea that it's ill-specified, that because there's details left out, that means it's not a proper algorithm, I don't buy that at all. And I don't think that anybody else who's taken an algorithms course really would buy that argument either. Because plenty of times in the past few lectures, we have defined algorithms where we've left out certain low-level details because they're sort of irrelevant. So consider when we were talking about, I don't know, Kruskal's algorithm. In Kruskal's algorithm, there is this one directive that says sort all of the edges into ascending order by weight. And when you saw Kruskal's algorithm, did you really think, oh no, this algorithm is not properly specified because you didn't tell me how to sort them? Well, I hope not, because I think we all know by now that it's possible to sort things. It shouldn't be necessary for me to enclose a complete implementation of merge sort every time I want to sort something. It should be completely valid for me to say, go and sort this via any means you choose. If I leave something general in my algorithm, it is, of course, up to you to choose a technique that makes sense. I am disclaiming liability if you choose a particular technique over another technique and it doesn't work out in your favor. But I also do have to be responsible for understanding that if I say, just choose an augmenting path via any means you want, I better make sure that my running time analysis doesn't assume that you're finding augmenting paths by some specific means. So similarly to how when we analyzed Kruskal's algorithm, we said, look, we all know how to sort, and so it's reasonable that we can do sorting in n log n time with merge sort. It isn't necessary for Kruskal to say that to us for us to understand that that's the case. But in cases where something general is going on, then yes, as we'll see in a few minutes, when I analyze the running time of this, I have to assume that our choice of augmenting path is the worst possible choice at each step because I have declined to give any guidance for how to do that. Another example of a place where we see a bit of generality in an algorithm is think about quicksort. It's pretty common in descriptions of quicksort, including the one that I gave back in lecture 9, to say, let P be some pivot. I don't even say what the pivot is. I just say, look, use a pivot rule to select a pivot. I leave the selection of the pivot rule to the person implementing the algorithm. This means that when I analyze quicksort, I have to assume that our pivot choice is as bad as possible, which we did. But there's nothing wrong with leaving a step like that vague, because I could always say, look, if we want to analyze quicksort in a specific case, go ahead and do that. But the overall structure of the algorithm is independent of exactly how I choose to select my pivot. And so I think it's perfectly reasonable, based on that precedent, to call this thing the Ford-Fulkerson algorithm. We do not have to give every minute step of the algorithm in fine-grained detail for it to be considered an algorithm. That said, in a minute I'll talk about one weird case where I suppose the people that propose to call it the Ford-Fulkerson method might have a good argument. Now, in the meantime, I should explain what I'm doing. Okay, so if you look at the overarching structure of what I have, basically the outer loop says, while there exists some augmenting path P, and then the inner loop says, perform an augmentation using that augmenting path. So walk along the path, look at every edge in the path, and then modify the flow to compensate, to account for the augmentation that I performed. But if you look at the inside of the loop, it does look sort of strangely complicated. Why does the augmentation take this many steps, and why are the steps sort of impenetrable? I have an example on the next slide, but I'm going to sketch out a quick example while we're looking at the pseudocode here. So basically the issue is just that I have to account for cases where I might know the capacity of the path. I might know how much flow I'm pushing along the path, but I don't know in advance, just when you hand me the path, I don't know in advance which direction the edges are pointing. So for example, I could have a case like this, where I'm pushing 5 units from V to U. I could have a case like this, where let's say I've got 2 out of 7 units available, so I've got a capacity of 5 available from U to V. I could even have a combination of both of these cases. So for example, in a case like this, the residual capacity from U to V is actually going to be 12. Because I can push 7 units from U to V, I can also send back 5 units. And so my augmentation procedure has to consider this. So let's hypothetically consider a situation where the capacity of my augmenting path is not 12. Let's suppose that it's 8. Okay, so how do I push 8 units from U to V? Well, the first thing I could do is I could work out the capacity available in the forward direction. So the capacity of the edge UV is 7. The flow along that edge is 0. So I can push up to 7 units from U to V directly along the forwards pointing edge. I want to push 8 units, but I can't do that across only this edge here. So this min function is saying, look, if you want to push more units than you have capacity for, for now, just push the amount you have capacity for. So the UV amount here ends up being this number, which is equal to 7. So I max out this. Okay, then how much do I push in the opposite direction? So that's the VU amount here. Well, I know in advance that the capacity of the path is CF of P. I assume that that is taken into account the residual capacity of every link along the path, which means it is feasible to push this number of units between any 2 vertices on the path. So that means that I will be able to succeed in pushing all 8 units. So the number I want to push in the reverse direction is just going to be CF of P, which in this case is 8, minus the amount I pushed in the forwards direction, which is 7, which equals 1. So I then push 1 unit backwards, and this ends up being 4 out of 5. That's why this looks sort of dense and confusing. I have an example that demonstrates that with much better handwriting on the next slide. So consider this flow network here. There is my source vertex S. There is my sink vertex T. Suppose that the first augmenting path I choose is this one. So I take 5 units and I push them all the way through this sort of zigzagging path up to vertex T. Now, how would I find that augmenting path? Let's take a look at the graph at the residual network before that step. Suppose I go and I find this augmenting path, this regular directed path from S to vertex T. Okay, so I perform an augmentation along that path, and then here is the residual network when I'm done. Now, notice this sort of interesting thing happening with these 2 edges in the middle. So the original residual capacity from, let's say, vertex V4 to vertex V1 was 5. I can push 5 units from V4 to V1. Symmetrically, I could push 5 units from vertex V1 to V4. But after the augmentation, one direction is now saturated. And what I realize is I can now actually push up to 10 units from V1 to V4, because I can push 5 units across the edge V1, V4, and also send back 5 units that are coming in from V4 to V1. So in my residual network, the edge from V1 to V4 now has capacity 10. Okay, so suppose I choose this as my next augmenting path. So that is, I traverse my residual network and I end up choosing this augmenting path. Okay, so what that corresponds to doing, if I look at the augmenting path, the capacity of the path actually is 10. I can send 10 units up here. I can actually also send 10 units from V4 to T, and it is possible to get 10 units from V1 to V4 in one step. I just max out the forwards edge and I zero out, I clear out the edge from V4 to V1. And so to account for that case, my augmentation logic is a little bit more complicated to allow me to push all 10 units across this gap here in one pass. Now, there are sources that want to avoid that case because it's sort of weird. That is, to avoid having to modify 2 edges at once to both clear out this edge and add stuff to this edge, they use a different definition of residual capacity that splits the augmentation into 2. So I guess the first augmentation would be zeroing out the reverse edge, and the second augmentation would be adding flow along the forwards edge. That's fine, and there are sources that do that, and that's completely valid. I'm choosing not to do that because basically all I'm doing is trading a little bit of complexity in the pseudocode in exchange for a simpler definition of augmenting path. So with my definition of residual capacity, which is also used by a few other sources, we end up with a bit of a cleaner definition of residual capacity that allows our augmenting paths to be found more easily. So with the definition we've been using, finding the augmenting path is still as simple as going and finding a directed path in my residual network. In exchange, I need a bit more complicated pseudocode, but it's not that much more complicated, and so I think it's a worthy trade-off. But there are some sources that don't do it that way. Fair enough. There actually are also some sources that fully prohibit this situation from occurring. That is, they say, in your original network, you are not allowed to have bidirectional edge pairs. I don't like that. And I'll talk about that again in about 20 or 30 slides. But basically, there are some assumptions that certain sources impose on the network, things that they don't allow to happen, that are convenient for the sake of talking about the problem, but really make a mess if you try and model real-world problems in terms of flow networks. So if you add certain constraints to your network, it does make it easier to prove theorems, but it also makes the network itself less useful. And I want to really avoid that situation. So I think allowing bidirectional edge pairs is just fine. Everything works out perfectly, except that my pseudocode is a couple of lines more complicated. Now, a claim that I really want to make here is that the flow that is produced by the Ford-Fulkerson algorithm is a maximum flow. But I can't prove that yet because, as I keep saying, as I keep alluding to, there is this really important massive theorem in the next lecture. So I hope you're ready for that, but until I prove that, I can't actually prove this claim. So we'll prove the correctness of the algorithm in the next lecture, as well as fully characterizing what a maximum flow is. Now, what I want to do with the rest of this lecture is talk about the running time of the Ford-Fulkerson algorithm, just so that we can get that off our plate before the next lecture. I also want to go back and sort of rewind a bit and talk about some assumptions we've been making through the entire lecture that are reasonable assumptions, but that do require our attention. We do have to explicitly acknowledge them. Okay, so first, the running time. At each step, so this loop keeps running as long as there is an augmenting path. So I guess the first question is, how do I go looking for augmenting paths in terms of the running time? Well, because we've already seen that a regular directed path in the residual network corresponds to an augmenting path in the original network, I could go find an augmenting path by using an ordinary graph traversal, so BFS or DFS. We'll see next time that BFS is a very good choice for this. And that would take linear time, linear in the number of vertices and edges. Now, this does require doing that traversal on the residual network, so we should take into account the time that's needed to create the residual network. And there are two ways to do this. One option would be to create it at the beginning and update it continuously. Another option would be to just create it again every time I need it. So at every iteration of the loop, create g of f from scratch and then do a traversal of it. I don't know that that's the most efficient thing to do in practice, but for the sake of analysis, let's assume that I do it that way. So constructing GF from scratch can be done in linear time. I can do it pretty straightforwardly using the current flow and the original network with a pretty straightforward linear time conversion. So I just iterate over all the vertices and pairs of vertices or flow values across valid edges and use that to create the backwards pointing edges where they're needed. It is also possible, if you don't want to actually create the residual network, to simply define a specialized version of a traversal algorithm like DFS or BFS that implicitly traverses the residual network using the original network. In other words, it walks backwards along edges that have a flow that's greater than 0. So it does the same thing we did originally before we defined a residual network. That's fine too. When I think back on the times I've implemented the Ford-Fulkerson algorithm or one of its variants, generally that's what I've done. The only times that I've explicitly constructed the residual network are for teaching purposes. That is, for the sake of making these slides, for the algorithms that I use to generate the graphics in the slides, I did construct the residual network because, I had to picture the residual network. But generally, I tend to use an implicit approach. So in any event, the total time I need to identify an augmenting path or to decide that there is no augmenting path is linear in the number of vertices and edges. And also, I actually am allowed to assume that the number of edges is greater than or equal to the number of vertices minus 1. Now, this requires a little bit of an argument, so I'm going to talk about that later. But basically, the reason I want to make this claim is because it allows me to ignore the v term. Because if e is greater than or equal to v, then then E just dominates the whole expression, so I can simplify things quite nicely. I will explain where I'm getting this from. It does require a little bit of logic. That is, there are networks I could construct where this doesn't hold, but I want to argue that if I construct such a network, it's useless. That is, the only parts of a network that are relevant are parts that are actually reachable from both S and T, and if that holds for all vertices in the network, then I'm guaranteed to have this. It's guaranteed that the underlying undirected graph underneath the directed network is is connected. It's a weakly connected directed network. Now, the augmentation itself pretty clearly requires at most size of E time. That is, in the worst case, the path itself contains all edges in the graph or some fraction of all the edges in the graph. The contents of this loop are pretty clearly constant. Finding the residual capacity of the path is not constant, but I only have to do that once. So I iterate along the path, find the residual capacity, and then performing the augmentation itself just requires time proportional to the number of edges at most. So the only remaining unknown, the only thing we have to work out then is how many times does the augmentation procedure need to run in the worst case before we're done, before the algorithm gets stuck and can end. Now, I suppose I haven't really established that this is a finite number just yet. I'm going to say that it is, and we'll talk about that in the next lecture. I will explain why to some extent now. There are actually cases where I might be in trouble as far as that claim is concerned, and I will talk about those in a minute. What I want to illustrate first, though, is an example of a worst case. So consider this flow network here. And suppose that I perform the Ford-Fulkerson algorithm on this flow network. Now remember that because I didn't say how we find the augmenting paths, I have to assume that the worst possible choice is always made. Because if there is a better choice of augmenting path that doesn't lead to bad behavior, I have to encode it into the algorithm to assume it's actually going to happen. I'm actually going to make a good choice. So I'm going to demonstrate a particular choice of augmenting path that's so terrible that it results in a really terrible running time and the most bizarre counterintuitive behavior imaginable. So here's my flow network. Maybe it's clear already that the maximum flow that I could ever expect to see in this network is going to have value 20. There's no way I could ever get any more than 20 units of flow to vertex T. Moreover, I can actually achieve that maximum. So if I send 10 units of flow along every edge on the outside of the square, I will get 20 units to vertex T. Okay, so that's going to be my maximum flow. I certainly can't get more than 20, and it's pretty easy to see that there is a way of getting 20. Let's perform some augmentations. Suppose that the first augmenting path I choose is this strange path, which only allows me to push 1 unit of flow because of this middle edge that has a bottleneck. Well, that's too bad, but fortunately now this edge is saturated. Well, not so fast. Suppose I go looking for my next augmenting path in my residual network. I go up to vertex V2, and then for some reason I go down to vertex V1. I'm allowed to do that. If we look at that edge, there is an edge from V2 to V1 in my residual network, and then I go up to vertex T. This corresponds to pushing flow backwards along the edge V2, V1. But I can do that. Okay, so I end up pushing 1 unit of flow backwards. Okay, so now T has 2 units of flow. And I think, okay, that's weird, but fortunately we should now be, on the fast track to getting to the answer. Nope, not so fast. Suppose I go looking for my next augmenting path. I go over from S to V1, and then I go up to V2. I take that same middle edge again, and I succeed in pushing 1 more unit of flow. And, this continues for a while. And so what I end up doing is pushing 1 unit of flow per augmentation over and over again, making just the barest amount of progress at each step until finally, after 20 iterations, I finally reach the maximum flow. So in this case, I required a number of iterations equal to the value of the flow. And in general, this is something that can happen. So I've shown that it can happen in one case, and for worst case analysis, that's enough. You could probably make all sorts of arguments about how this is ridiculous, but yet you have to agree, I do have you on the fact that this could occur. So there is a graph, and there is a sequence of augmenting paths that produces this weird behavior, and I can make this as bad as I want. So for example, if I set the capacity of these edges to 1,000, then it's going to require 2,000 iterations to get me all the way to my maximum flow. In general, what I've established is that the running time of the algorithm in the worst case could be this. It could actually be the number of edges multiplied by the value of a maximum flow. You'll see that I used a big theta there, and I can justify that pretty easily, which is that the claim I'm going to make is that when all of the capacities are integers, so I have no need for real numbers or fractional values, then every augmenting path will allow me to push at least one unit of flow through the graph. And that means that if I have my maximum flow is supposed to have this value here, then I will always make progress of at least one unit of flow at each augmentation. And therefore, that I will never need any more than this number of steps, because the minimum progress I can make is to push one unit of flow. I just showed my worst case example where I actually attained that minimum, but it can't get any worse than that. So the running time ends up being number of edges times value of the maximum flow, which is sort of unique. I think we haven't seen this yet. I think maybe this showed up in the context of convex hulls about 1 million years ago. But other than that, we really haven't seen very many algorithms of this form during this course. It's what's called an output-sensitive algorithm, an algorithm whose running time depends on a parameter of its output, not just a parameter of its input. The closest thing to this that we've seen recently, in my mind, is that dynamic programming solution for subset sum. So for the subset sum problem, we were able to derive this algorithm whose running time was n, the size of the input, multiplied by one of the input parameters, the goal sum w. So w is part of our input, but not our input size. Normally, we like to parameterize our running time by the size of the input, so like n to the fifth, or the number of vertices plus the number of edges squared, the size of the input, not the specific values of the input. But that subset sum algorithm, and in its running time, actually had one of the input values, which is just some number w that was provided as part of the input. And so the algorithm for subset sum is very sensitive to the specific characteristics of the input values, but it's not like this. It's not output sensitive. Somebody who's using the subset sum algorithm would know in advance when they provide a very large value of w that the algorithm might be slow. Whereas it might not be possible in advance to know what the value of your maximum flow is going to be. So you don't realize that the algorithm is going to run slowly until after you've run it, until after it's already been started. And that's one of the dangers of output-sensitive algorithms. Even back in the context of convex hulls, where we saw a sort of output-sensitive algorithm, it wasn't that big of a deal because we were able to bound the running time of that algorithm because we knew certain things about the way the algorithm worked, about the size of the convex hull in the worst case. Whereas here, if I just look at this graph, I suppose with this graph, it's sort of clear that the maximum flow is going to have value at most 2,000, or maybe it will be 2,000. But in general, you can't necessarily glance at the graph and figure that out. You could come up with a pretty reasonable bound, but in general, you can't guess that just by looking at the graph. So since the value of the maximum flow is not constrained to any function of the input size, like the number of vertices or the number of edges, this is not constrained to be polynomial or even exponential necessarily in the context of the input size. It could be catastrophically slow. So if the value of the maximum flow is something like, exponential in the number of edges, well, then the algorithm would be exponential in the input size. Now, you could easily look at this, as I mentioned a minute ago, and say, yeah, whatever, this is a contrived example, and you made just a ridiculous choice of augmenting paths. With even the most basic pathfinding logic, we could do better than this. So, for example, you might propose that if I'm looking for an augmenting path and I see the vertex t, I should always go there directly. I should never take an edge that goes somewhere else if, from the point that I'm starting at, like v1, there is an edge that goes to t. And if I did that, you'll observe that I would pretty much immediately saturate this edge and this edge. My next augmenting path would go through here and saturate both edges. And you're right. If you chose that heuristic as a way of finding augmenting paths, you wouldn't have this problem. But unfortunately, I've got a few tricks up my sleeve. I could easily design a graph that suffers from the same condition of this graph and defeats that heuristic. The heuristic I'm talking about here is the one where if you are looking for a path from v1 and you see the goal vertex t, just go directly there. I can arrange it so that you can't see the goal vertex t easily enough. I could just add one extra vertex here. That way, from the point of view of v1, you don't know which of the two edges will take you to t most quickly. It's not obvious from that point of view. But you could look at that and say, whatever, there's a way around that too. So why is it that every single time you chose an augmenting path during this example, you chose this edge here that had capacity 1? Why not use one of these edges with large capacity? So one other pathfinding heuristic is as you go through the graph, the paths you look for first are always going to be along edges with high capacity. You always explore the low capacity edges last, as a last resort. And it's also true that in this graph, that pathfinding heuristic would defeat my example. That is, you'd find this augmenting path, then you'd find this augmenting path, and then you'd be done. You wouldn't get worst case performance. The problem is that's still just a pathfinding heuristic. It works around this problem for this graph, but I could create graphs that still defeat that heuristic. So it's tempting to try and remedy this with what I'm calling sort of derisively heuristics. I mean, heuristics are a great idea. You should use them, but you can't count on them to solve all of your problems unless you can write me a proof that shows that they always work. So for example, you could choose to always explore a high capacity edge before a low capacity one. And in this example, that would help you. What about this example, though? So here, suppose that you use a heuristic that says that if you're looking at multiple candidates for the next edge to transit, you always take the high capacity one. So I walk from S to V1, and I have two choices. Either I go up here, or I go to V3. Now you could say, hey, wait a minute, T is up here, go there first. Fair enough. Suppose I add an extra vertex along the way to stand in the way between U and T. So your choice is to go to some anonymous other vertex here, we'll call it V6, or to go to V3. What do you choose? Well, to avoid that example we just saw, I guess you're going to choose this high capacity edge here. But notice that once you do that, you're now in V3 and you've fallen directly into my trap. Because this high capacity edge was a ruse, and once you get to V3, you're stuck with this low capacity edge after all. And so basically the issue is, even if you derive some kind of heuristic, I can just add a couple of layers of indirection and break your heuristic. I can reverse engineer your heuristic to create the same issue that you were trying to avoid by just boxing you into a position where you have to make the bad decision that you were designing the heuristic to get around to begin with. So too bad. Now that said, it actually turns out there is a faster algorithm. There is a way of refining your pathfinding such that you are guaranteed to find the maximum flow in polynomial time. We'll talk about that in the next lecture. And it turns out that the trick we need to use is actually even simpler than the heuristics I just proposed. It's just that it's a much more structural technique. It doesn't have to do with which edge you choose at a particular step. It has to do with more complicated things like the number of edges in the paths that you choose and the order in which you consider those paths. But that's one of the other big outcomes of the next lecture. So the slides are going to catch up with what I just said. If our traversal algorithm gets here, a heuristic that chooses the higher capacity edge first goes to V3, and then you can verify to yourself that it falls into the same trap that we set in the previous example. And so we have no choice but to conclude that this formulation of the algorithm, of the Ford-Fulkerson algorithm, indeed has this running time, number of edges multiplied by the value of the maximum flow. Now, that's still progress. So we haven't yet seen the proof of correctness, but if we believe the algorithm is correct, then we have indeed found a way of solving the maximum flow problem. Now, actually, it gets a little bit worse. There's one case I've been avoiding, which is it turns out that this running time only applies in the cases where your edge capacities are actually always rational numbers. And the reason for that is that implies that every augmentation will increase flow by some minimum amount. So in the case where all of the edge capacities are integers, then it's pretty, well, easy isn't the right word. It's a little bit tedious, but it's within our reach to write a proof that shows that if the capacities of every edge are always an integer, then every augmentation will increase the total value of the flow by at least 1. And if that happens, then you are guaranteed to reach the maximum flow value in a number of steps that is proportional to this number here. If our capacities are arbitrary rational numbers, so if this is 1 over, I don't know, k, where k equals 4 over 5 or something, you can actually prove something similar. If they're always rational numbers, there's going to be some pre-existing minimum increment that you can assume that the flow will increase by with every augmentation, which is sufficient to show that the number of steps is going to be finite on the one hand, and it's going to be relatively predictable and proportional to the value of the maximum flow. But it's only if the edge capacities are rational numbers. If you take a step back and think about that, though, when was the last time you worked directly with a truly irrational number in a computer? Because every time you write code, you probably use data types like int, and you use data types like float. And if you want to represent a rational number like 4 over 5, you might use a pair of ints. If you want to represent a real number, what you typically do is use an approximation. So I might want to represent the real number pi, and we know that pi in an abstract sense is irrational, but this, 3.14, is a rational number, and this, 3.14, 3.1415 is also a rational number. And in fact, any finite approximation of pi is in fact a rational number, 3.141592 or whatever. And so any representation of numbers that you're likely used to, that you use in general cases like float or double or int or long int, those are actually all rational numbers. Even the ones that appear to be real numbers, they're just approximations that deep down are rational numbers. There are ways inside of a computer to talk about actual truly irrational numbers, but they require, a bunch of extra machinery, a bunch of basically symbolic algebra tools. So you could implement the Ford-Fulkerson algorithm in those cases, and you would actually run into trouble in those cases. But because that's relatively unlikely in our context, I'm going to write that off as a very unusual special case and simply declare that for our purposes, the Ford-Fulkerson algorithm, where all of the edge weights, all the edge capacities are rational numbers, does finish in a finite amount of time, and it has this running time in an abstract sense. So in the case where all edge capacities are integers, it's pretty straightforward, maybe a little bit tedious, to show that every augmentation must increase the flow by at least 1. Because if the augmentation increases the flow at all, the smallest integer you can have that's greater than 0 is 1. If the edge capacities can be truly irrational numbers, so if you run the algorithm on paper, or if you have some toolkit that allows you to talk about purely irrational numbers in a fully abstract symbolic sense, then actually there are cases, and if you look up the algorithm on the internet, you can actually, people will give you examples of cases where this can happen. There actually are cases where the Ford-Fulkerson algorithm might never terminate. It'll only asymptotically approach the maximum flow. It'll never actually get to it. And that's due to the weird way that irrational numbers works. And so in this context, the people that call it the Ford-Fulkerson method actually have a good point, because way back in lecture 1, we defined that something is not an algorithm if it doesn't finish. And so I suppose I have to concede that they do have a point about that after all. But in our context, it's reasonable to call it an algorithm because we don't yet know how to deal with purely irrational numbers inside of a computer. So we'll see in the next lecture that in any event, it is actually possible to find a maximum flow in polynomial time by doing what amounts to a completely trivial specialization of the path selection step. So the difficulty of the more complicated variant of the algorithm isn't finding the path. It turns out we can do that very easily. I won't spoil it, but it's very easy. It's that we then have to write a proof that shows that that path selection step does indeed give us a polynomial time algorithm, not an output sensitive algorithm like the general Ford-Fulkerson algorithm. Okay, so that's the end of the main material for this lecture. Before we move on to the next lecture, I do want to attend to a bunch of special cases just to get them out of the way. I want to talk about some assumptions that we made and talk about whether it was reasonable to make them, it turns out that it was, and whether we're losing anything by making those assumptions. First assumption. Deep down in this entire lecture, we've had this assumption that edges like this are basically irrelevant. Edges that go into S or out of T are basically irrelevant. That's a reasonable assumption. All of the augmenting paths that we have found, and by our definition of augmenting paths, all of the augmenting paths we're ever going to find would never include an edge like this. Why? Well, because our augmenting path must begin at vertex S. And if it included an edge that went back to vertex S, then what would it be? Well, it might look like this. It'd go from S to V1 to V2, back to S, and then, over to T. But that's not a path. A path cannot contain the same vertex twice. And so if we try and find a maximum flow via augmenting paths, we're never going to go from vertex S back to vertex S. And similarly, if we get to vertex T, we're going to stop. That's the end of our path. We're not going to keep walking and walk back around. So for our purposes, for the Ford-Fulkerson algorithm, edges that go into S or out of T are irrelevant to us. But are they harmful? And the answer, it turns out, is no. So since all flow originates at S, we gain nothing by routing flow back into it, but we can if we want to. And similarly, we gain nothing by routing flow out of T. What's the point of doing that? We want to make sure that the flow stays at vertex T. And so it makes sense for our purposes for designing algorithms that we'll never need edges like this. But the question is, should we ban them? Should we say that such edges aren't allowed to exist? Are these edges harmful? And I think the answer is very clearly no. So under our definition of a flow network, it is possible for a flow to have a valid flow assigned along edges like this. It's even possible for a maximum flow to actually have flow routed along this type of edge. So consider this flow here, which happens to be a maximum flow. This is one of the flows that we saw earlier. We haven't proven that yet. That's why it says this here again. We'll show that in the next lecture. It turns out our condition is actually very easy once we know what it is. So here's a maximum flow. Notice that in this maximum flow, none of these edges are carrying any flow at all. None of the edges out of vertex T or into vertex S. But that said, I could create another maximum flow with the same value 10 that does do that. So what about this one here? Nothing is stopping me from routing an extra 1 unit of flow in a circle from vertex S back to itself. If I augment my flow with 1 unit along, well, okay, so S, V1, V2, V3, S isn't an augmenting path because augmenting paths have to end at T. But augmenting paths are a device that we use to find maximum flows. There's no requirement that people that create flows in flow networks have to use augmenting paths to do so. So if I route 1 unit of flow from S back to S along this closed path, notice how the result is still a maximum flow. It's still feasible, and it still has value 10. It just wastes a bunch of time routing flow in a circle. That's fair enough, though. That's benign. It's weird, but it's not harmful. And so I adopt the convention of live and let live, I guess. Similarly, nothing is stopping somebody from sending 6 units of flow out of vertex T and then having them loop back around and end up back at vertex T. If you compute the value of this flow, it's still 10. There are still 10 units that end up at vertex T, even though a few units take a field trip to get there. That's fair enough. I'm allowed to do that. It's weird, but I am allowed to do that. Now, the Ford-Fulkerson algorithm is never going to do this because it works with augmenting paths, and it's not a path if it starts at S and ends at S or passes through S anywhere in the middle. So although this situation can happen and is valid, it will never happen with the Ford-Fulkerson algorithm. So the maximum flows that algorithm finds will always have zeros on edges that point into S or out of T. There are some sources that explicitly prohibit this from happening. So they explicitly say you are not allowed to have edges whose endpoint is S, and you're not allowed to have edges whose source vertex is T. I think that that's really oversimplifying things. So as I mentioned earlier, it does make sense if you're writing a textbook or frankly giving a lecture on the subject to add a bunch of extra restrictions to make your definitions easier and therefore easier to explain. However, if you do this, you make the problem less practical. You make it much harder to model real-world things using your modeling technique. And so if these edges are harmless, let's allow them. So it's true that by prohibiting them, it makes it easier to define the value of the flow. So the definition that I gave for the value of the flow about an hour and a half ago was you take all the flow leaving vertex S and you subtract all the flow coming in, which is, I don't know, a little bit more complicated than what other sources might do. So some sources which prohibit inbound edges to S are able to define the value of the flow to simply be the amount of flow leaving vertex S because it's impossible for flow to come back in. Okay, so you've just made one definition a little bit simpler, although not that much simpler, in exchange for significantly restricting the applicability of the problem. So I oppose that. I think it's fine to allow edges to point into S. And most sources also do. There's very few sources that I've seen that prohibit those inbound edges. Okay, so one other assumption. The flow network is basically connected. I say basically here because we know that the whole connectivity thing on directed graphs is a bit of a can of worms. I suppose one way of framing this is that it's sort of weakly connected, although even that isn't quite capturing what I want to convey here. Really what I care about is if I expect a vertex to be useful to me at all, that means that there must be some chance I might one day push flow through that vertex, which means there must be a path from vertex S to that vertex and a path from that vertex to vertex T. If not, there is no way that I'll ever pass flow through that vertex. It's reasonable to assume, therefore, in our flow networks that all vertices that we care about have a path from S to that vertex and a path from that vertex to T. And what this implies basically is that the underlying, if I collapse the graph down to an undirected graph and look at it, it's connected, and therefore that I get this, which applies to all connected undirected graphs. That condition actually applies to this graph too, even though, as we'll see in a minute, this graph has a sort of weird problem. If we look at these 4 vertices, you'll notice that this cluster of vertices superficially does seem to be tied into the rest of the graph. But if you look at it closely, you'll observe that all of the edges out of this cluster, or all of the edges between this cluster and the outside world, are pointing outwards. There is no path from vertex S to any of the vertices in this cluster. And that means that on any feasible flow in this graph, there will be no flow passing through these vertices. Or actually, no, I guess there is one sort of weird special case. So I suppose I could have a graph with 3 isolated intermediate vertices that just have flows circulating around ad infinitum between them. So like this. So if I want to, I guess, flow is still conserved if I send the same 1 unit of flow infinitely in a circle between these 3 intermediate vertices. I suppose that could happen. But in any event, these vertices will never be relevant at all to any maximum flow from S to T. I will never need them for a maximum flow. Even if they could participate, it would be superficially. And that actually means, because they're irrelevant to the flow calculation, if I wanted to, I could basically delete them. So since there is no path from S to any of these vertices, no augmenting path will ever pass through them, and so I can completely ignore these vertices when I go to find augmenting paths. In fact, if I wanted to, I could just eliminate them from the graph before I start. So before I do any flow computations, I could identify which vertices are unreachable from S, or which cannot reach T, and just get rid of them. Just delete them altogether from the graph. And deleting them might take a little bit of time as a pre-processing step, but it would save me a bunch of extra trouble of having to iterate over them over and over again later as I look for augmenting paths. So that's one issue. But of course, I could also, in the spirit of live and let live, I could ignore them. Certainly in any event, it's valid to expect that a network like this could be an input that I should have to work with. Whether I choose to delete these vertices myself is my business, but it is reasonable that if these vertices exist, that's no big deal. And there might be sources that say, oh, that's never allowed because why would you need such things? I don't know why I would need such things, but a lot of real-world applications have all sorts of weird redundant or vestigial features. I don't want to have to police that. It's better to allow harmless extra cases to exist and just ignore them. Okay, so one last case, one assumption that we often make, and this is true of all algorithms because we're used to looking at examples that are sort of intuitive, is that the network is designed without redundant or vestigial or irrelevant features. So if you look at the vertices over on the left in this graph, they're sort of weird. And the issue is, it's useful in my slides and when people try and explain things to you or when you read a book to use well-behaved examples. If I want to talk to you about what it means to push flow from S to T, I'm probably going to give you a sort of intuitive example where the graph makes sense. I'm not going to have all these extra vertices over to the left that are sort of, technically connected to the graph but appear to be sort of useless. The problem is that for real-world applications, this is really common. So suppose I want to solve a lot of problems on the order of, I want to get something from one vertex to another in some large pipeline network. I might create a pipeline network, a real-life pipeline network, I don't know, where each of the vertices represents a city or something, and I model the network as a graph, and only after I've built the pipelines do I decide what my source is and what my destination is. A lot of real-world pipeline networks have that property. You build the pipelines between different places, but they're not always in use. Maybe only when there's a shortage of water do I want to begin routing water through the water flow network. And so I've built this whole pipeline network, and only after I've built it do I select that this is my source vertex. And that selection might result in weird, bizarre, redundant features becoming apparent. They could be features like what we saw earlier, like things like this. It could also result in there being edges inbound to my source vertex, which I already said I think are harmless. So in this network, with this choice of source vertex and this choice of sink, all of these vertices are sort of vestigial. They can't be deleted like in the last case, because you'll observe that there is actually a way to reach all of these vertices from S. I can go from S to V2, and to V3, and to V1, and down to V4. And similarly, I can actually reach T from all of these vertices. So for example, I can go from V1 down to V4. Oh wait, that's a dead end. I can go from V1 up to V2, down to V3, over to S, up to V5, and down to T. But it's also pretty obvious that any path that takes these vertices to T involves S. So why would I bother doing something like this? Although I can, why would I bother following a path from S to T that went through S again? So a walk from S to T that went back to S. That doesn't make any sense. That's redundant. So just because these features exist doesn't mean I have to use them, but it doesn't mean that they're really that much of a challenge for me either. So there's no benefit to including any of these vertices in a maximum flow, although we could create maximum flows that do route flow through these vertices. And actually a good exercise to to try just on the way out of this lecture is compute a maximum flow of this graph using the Ford-Fulkerson algorithm, and then take the maximum flow you end up with and modify it so that it's still maximum, but where there is flow being routed through, I don't know, maybe all of these other vertices. See if you can make that happen. So although these don't need to be here, I could delete them if I have some way of knowing in advance that they're redundant. I could just leave them there. If I have no easy way of singling them out and getting rid of them, I could just leave them there. And I certainly shouldn't prevent them from existing, because the more restrictions I add, the less practical my application becomes. The less likely it is I could use my algorithms to solve some real-world optimization problem. And in general, as I've mentioned before, real-world optimization problems are often a complete mess. They're full of all sorts of features that we have to work around. They might work against us, they might be benign. We have to work around them because, real life just isn't as, pleasant as this theoretically pure setting we find ourselves working in. That's as good a place as any to end the lecture. So next time we're going to talk about two key things. One, what is a maximum flow and what does it mean to identify it? And then two, how can we get the running time of our Ford-Fulkerson algorithm, which by the way will be proven correct by the theorem that allows us to identify maximum flows. How do we get the running time of that algorithm down to something polynomial? Both of these are amazing, profound results, among the most profound results we're going to see for this entire course.